Okay, let's dive right into this explainer and demystify exactly how AI handles the incredibly vast acoustic differences in human voices. Think about it for a second. Every time your phone perfectly transcribes a rushed text message while you're speed walking down a noisy street, you are directly benefiting from decades of really heavy lifting in signal processing. Today, we're exploring a fascinating cornerstone of that technology. It's called fMLR, and it essentially acts as the sci-fi universal translator of speech recognition. This is literally the mathematical magic that paved the way for the instant transcriptions we all just take for granted now. We have a pretty clear roadmap today to break down this complex concept logically. We'll cover the speech recognition problem, the universal translator analogy, how fMLR actually works, the two-pass decoding catch, a quick comparison of fMLR, MLLR, and MLLT, and finally, the neural model era.
All right, section 1, the speech recognition problem.
So, have you ever wondered why a high-pitched Southern drawl or a really deep British accent used to cause sudden, almost hilarious errors in transcription software? Well, an acoustic model is originally trained to recognize specific phonemes, right? Those are the distinct foundational sounds that make up our words. But human voices are incredibly, and for engineers, frustratingly, diverse. If a model expects a crisp, sharp vowel, but instead encounters a Southern drawl where that exact same vowel stretches lazily across a few extra milliseconds, the raw acoustic data looks completely alien to it. Or if a deep British accent shifts the pitch way down into a frequency band that the model associates with, say, background rumble, it gets confused. When you say the word hello, the raw mathematical shape of that audio is totally different than when I say hello. When we look at the actual physical acoustic hurdles, things like vocal tract length, your pitch range, and accent variations, we start to see exactly why these models trip up. I mean, if your vocal tract is physically just a bit longer or shorter than the average person's, the fundamental frequencies of the sounds you make naturally shift up or down. To an acoustic model just trying to do its job, these unique, beautiful human characteristics look like erratic noise. They literally scatter the same target phoneme across completely different data regions. So the absolute crucial takeaway here is this. Before an AI can figure out what you're saying, it has to somehow strip away how you're saying it. Moving right along to section 2, the universal translator analogy. Enter fMLLR. Okay, yes, it stands for Feature Space Maximum Likelihood Linear Regression. It's quite the acronym soup, but at its core, fMLR is just an ingenious mathematical technique to normalize acoustic features away from individual quirks. Technically speaking, it's a per-speaker affine transform. Now, if that sounds intimidating, don't worry. Just think of taking a piece of acoustic clay, which represents your unique voice, and mathematically stretching, rotating, and shifting it until it fits perfectly into a standardized, pre-made mold. And it does this without changing the actual volume of the clay or the core message of the words. It's a totally custom adjustment, calculated for your specific voice, applied directly to the acoustic features coming into the mic, moving them toward a shared canonical space. You can really think of this canonical speaker space as a sci-fi universal translator for your vocal tract. Except instead of translating alien languages into English, fMLR translates your specific pitch, the physical length of your vocal tract, and your regional accent into one uniform, completely average speaker profile. It essentially asks the system, hey, what would this audio sound like if it were magically spoken by the perfect, average, slightly robotic speaker that the model was trained to understand? The relief for the acoustic model is massive. It doesn't have to learn 10,000 different global accents anymore. By normalizing away your specific speaker characteristics, the AI just sees clean, neutral features and instantly recognizes the underlying phonemes. Section 3, how fMLR actually works. So how do we actually do this? It all comes down to a remarkably elegant transformation formula. O hat equals A times O plus B. Now please don't let the math scare you away. In this equation, O is your original 40-dimensional feature vector. And don't let 40-dimensional throw you off either. Just imagine 40 different acoustic sliders, like a graphic equalizer on a really high-end stereo system, that capture the unique texture and frequency of a tiny millisecond slice of your voice. A is just a 40 by 40 matrix, and B is a 40-dimensional bias vector. By doing a simple matrix multiplication and adding that bias, fMLR mathematically rotates, scales, and shifts those 40 sliders. It's literally taking your unique acoustic data cloud and dragging it directly over the average speaker's cloud. And honestly, the sheer efficiency of this process is what's truly staggering. To pull off this incredibly complex normalization, the system only needs to learn about 1,640 numbers per speaker. That's the 40 by 40 matrix, which is 1,600 numbers, plus the 40 numbers in the bias vector. That's the whole shebang. Those 1,640 numbers perfectly capture how to map your voice into the canonical space. It makes fMLLR an unbelievably cheap and efficient mathematical transform. Once it's calculated, the system just reuses it for the entire duration of your audio without burning through extra computing power. Which brings us to Section 4, the two-pass decoding catch. Because here's the kicker. Despite being computationally super cheap to apply, fMLR introduces a really annoying operational hurdle in the real world. You can't just apply fMLR blindly the second someone starts talking. To calculate those magical 1,640 numbers, the system has to know at least a little bit about what you are actually saying first. It needs a baseline alignment to figure out your accent before it can mathematically translate it. Because of that, fMLR absolutely requires a two-pass decoding process. In Pass 1, the system just does its absolute best to decode the raw audio, giving it a rough, probably error-prone guess. Then, it uses that rough first pass to figure out your specific transform matrix. Finally, it applies the transform and runs a second, highly accurate pass. If you remember using early voice-to-text on an old smartphone, you know the feeling. You'd speak, the phone would pause and think for a few agonizing seconds, and then, boom, a whole sentence pops up. That latency, that annoying delay, that was exactly this two-pass requirement in action. And for real-time transcription, it was a massive headache.
All right, Section 5, fMLR versus MLR versus MLLT.
If you ever read the older research papers on this stuff, the naming conventions are incredibly messy. So let's clear up the classic confusion right now. The differences really come down to their targets. fMLR, which is what we've been geeking out about, transforms the incoming acoustic features into a neutral space. It adapts to the speaker. Contrast that with the older MLR. Notice there's no lowercase f there. MLR transforms the model means instead. It operates directly inside the AI model, which requires way more parameters to adjust the AI to fit your voice, rather than efficiently adjusting your voice to fit the AI. And then there's MLT. Despite the suspiciously similar name, MLT isn't even speaker adaptation at all. It's literally just a global math rotation applied to the data for everyone. So, easy cheat sheet. fMLR adapts features, MLR adapts models, and MLT just globally decorrelates data.
And finally, Section 6, the neural model era.
So, where does fMLR fit into today's tech landscape? Well, as deep neural networks completely took over, the fundamental strategy shifted dramatically. The classic fMLR approach was all about normalizing the incoming features to look perfectly average, which forced that costly, latency-inducing two-pass decoding. But modern neural networks totally sidestep that. They avoid the two-pass latency entirely by replacing fMLR with what we call I-vectors. An I-vector is roughly a 100-dimensional speaker embedding. Think of it as a super concise, instantly readable mathematical fingerprint of your voice. Instead of trying to mathematically erase your unique traits to fit an average mold, the system just feeds this fingerprint directly into the AI. The neural network uses it dynamically in real time to adjust its internal weights to your accent. It's a brilliant paradigm shift. We went from normalizing the features to simply informing the network about who is speaking, all in one seamless, single pass.
It's wild to think about, right? We moved from this brilliant mathematical workaround of forcing our incredibly different voices into a single average box to robust neural networks that just accept a snapshot of who we are to understand us instantly. I really hope this explainer leaves you thinking about the massive leaps speech recognition has taken, from those agonizing multipass delays to the real-time flawless captions we use today. As AI keeps evolving from standardizing our traits to simply understanding them instantly, it makes you wonder, what other foundational workarounds are just waiting to be rendered totally obsolete? Keep questioning, keep exploring the math behind the everyday tech, and thank you so much for joining me for this explainer.